Okay, October, November 2019, paper 6, variant 2. Question 1. A student investigates a pendulum. Figure 1.1 and 1.2 show some of the apparatus used. A student adjusts the length of the pendulum until the distance d is 50 centimeters. State one precaution that you would obtain, okay, that you would take. One very important precaution in this experiment would be what? Yes, taking the reading perpendicularly to avoid the parallax error. Okay, so take the reading, take the reading perpendicularly to avoid the parallax error. Student displaces the bob slightly and releases it so that it swings. Figure 1.2 shows one complete oscillation of the pendulum. He measures the time for 20 complete oscillations. The time t is shown on the stopwatch. In the first row of table 1.1, record the time shown. So we need to write down the time shown in the next page, 27.60. I'll write it down as 27.60. Why? Because all of the readings are 4 significant figures. And then I need to write down the the period. Period would be dividing this time by what? By 20. Why? Because you have 20 complete oscillations. So 27.6 divided by 20. This would give you a period of 1.38. 1.38. Then t squared slash s squared. We need to find the square, 1.38 squared. So what is 1.38 squared? It is 1.90. 1.38 squared is 1.90. Plot a graph of t squared slash s squared on the y-axis and d slash centimeters on the x-axis. So t squared slash s squared. And then d slash centimeters on the x-axis. d slash centimeters on the x-axis. You do not need to start the axes from 0 and 0. Okay, fair enough. T squared started with 1.9 all the way to 3.96. 1.9 all the way up to 3.96. So I guess we might start with 1.5 and increment 0.5. Yeah, sounds about right. 1.5, 2.0, 2.5, 3.0, 3.5, 4.0. Yeah, just about right. And then on the x-axis, the distance 50, 60, 70. Okay, we can just plot them as they are. So 50, 60, 70, 80, 90, and 100. Yeah. Let's plot the points using small x's. Using small x's. So first of all, 50 and 1.9. 50 and 1.9. Where's 1.9? Here is 1.9. This is 1.9. 60 and 2.25. 60 and 2.25, which is exactly at this point. 70, 2.76 or 2.75. Here is 2.75. 80 with 3.20. 3.20 is exactly 4 squares above 3.0. 90, there is no 90, but there is 100, and 3.96. So 103.96, which is 1 square just below 4. Let's draw a line of best fit. Okay, this is a line of best fit. Yes, this would be a straight line. This would be a straight line. It doesn't have to pass through all of the points, not at all. Okay, Doesn't have to pass through all the points. It just needs to pass through most of the points. Okay, if it even passes through one point, it would be sufficient, but you need to make sure that the points above the line are equal to the amount of points below the line. That's all you need to do. Okay, let's draw them. I can use this line, which is a straight line, to pass through the points this way. Yes, I might have 1 point above, or 2 points above, and 2 points below. This would be a really good line. So the first point, 50 and 1.9, and you have all of the points following it. Okay? Then we need to find the g, the gradient. Can I find the gradient of the graph? Yes, I can find the gradient by drawing the triangle. You have to draw the triangle on the graph, joining the two furthest points as such. When we join these points, how can I find the gradient? Rise over run, y2 minus y1 over x2 minus x1. So y2 is 3.96 minus 1.9 over 100 minus 50. You should write this in the space below. Okay, I'll just remove this line. I'll remove this line and I'll write this down in this space below. So 3.96 minus 1.9 over 100 minus 50. This gives you a gradient of 0.041. 0.041. Yes, you do have a range. And now, for the next question, calculate the acceleration of free fall in grams per in meters per second squared, where g is 0.395 over g. Basically, 0.395 over the gradient, which we just found, which is 0.041. 0.041. If you use your calculator to find the g, it would be around 9.63. 9.63, which is acceptable, yes, because we know that the acceleration is what? We know that the acceleration is 9.8, which is correct. Question 2. A student determines the resistance of a resistance wire. She uses the circuit shown in figure 2.1. She measures the current I. What is the current I in this question? 0. Yes, 0.56. 0.56 amperes. 0.56 amperes. She places the sliding contact C at a distance of 20 centimeters from point P. 20 centimeters from point P. She records the potential difference. Calculate and record R. Can I find the resistance? R equals V over I. So I have the voltage. R equals voltage 0.6 and the current was 0.56. Current was 0.56. The resistance would be 1.07. 1.07. And then we need to complete the table headings or the column headings. Voltage slash volts, resistance slash ohms. Okay, volts and ohms. Look carefully at the values of L and R. Tick one box to show your conclusion from the results and justify your conclusion. Think about what's happening. R, when R is increasing or when L is increasing, what's happening to the resistance? As the length increases, the resistance increases, yes. So R is directly proportional to length. So R is directly proportional to the length within the limits of experimental accuracy. Okay. As the length increases, the resistance increases. We need to include some of the values. All you need to do is include some of the values. So how can you include some of the values? You can say when the length was 20, the resistance was 1.07. When the length was 100, the resistance was 4.96. Okay. When the length was equal to 20, R was equal to 1.07 ohms. When the length was equal to 100 centimeters, the resistance was equal to 4.96 ohms. Let's make sure these are the correct numbers. Yes. Use the values to estimate. Can I find or estimate the potential difference across 50 centimeters of the resistance? Yeah, 50 centimeters. Do I have 50 centimeters? No, I don't have 50 centimeters, but it's in the middle. It's right between 40 and 60. It's right between 40 and 60. So what should I do? I can find the average of these two numbers. You can find the average of these two numbers. Basically, 1.96 plus 3.05 divided by, I'm sorry, we need the voltage. I'm sorry, not the resistance. Okay, 1.1 plus 1.71 divided by 2. Okay, so basically you want the average, you want something in the middle. So all you need to do is 1.1 plus 1.7 divided by 2. 1.71 divided by 2. This would give you a voltage of 1.40 volts. Okay. Can I use cross multiplication? Yes, you can use cross multiplication. Um, might not give you an exact number. Okay. 1.1, 1.7. Yeah, it could maybe. Anyway, calculate the resistance of 50 centimeters of the resistance wire using R equals VE over I. You have the VE, you have the estimate, and you have the current. So all you need to do is divide 1.4, 1.40 divided by 0.56. 1.40 divided by 0.56 will give you a resistance of 2.51 ohms. Why did we divide by 2? Because we found the average, because 50 is right between 40 and 60. Basically, it's as if you said 40 plus 60 divided by 2. So this is 50. All you need to do is do the same with the voltage. Do the same with the voltage. Does the current change when the sliding contact changes? The current could change, but for this question, he's saying that the current is constant. So I don't care, honestly. Okay. Where did we get the 0.56? The current, which we found in the beginning of the question, 0.56 amperes. It's the same current. Okay? Yeah. In this type of experiment, it is sensible to keep the temperature of the resistance wire as close to room temperature as possible. Okay? It's just one simple way to minimize the rise in temperature. How can you decrease the rise in temperature? All you need to do is what? Yes, switch off the current between the readings. That's all you need to do. Switch off the current between the readings. Or someone could say you can lower the current. Yeah, you could do that. But it's more sensible to just switch off the current. Okay, switch off the current or the circuit between each reading. Circuit between each reading. Okay. How do I find the average? You find the average by adding numbers and dividing by the number. You have two numbers, so I added them and divided by two. Why should I switch off the circuit between each reading? Because if you keep the circuit on, the wires could get hotter, and if the wires get hotter, it would give you a higher resistance, and that's why it would be sensible to switch off the circuit between each reading to keep the temperature at to keep the temperature of this wire at room temperature. Okay. Question 3. A student determines the focal length f of a lens. He places the screen at a fixed distance. Okay, so the distance between the screen and the lens is v, distance between the object and the lens is u, the total distance is d. On figure 3.1, measure the distance using your rulers. If I use the ruler, the distance between them should be 8 centimeters. I know if you actually measure it, if you print out this exam and you measure it, it might be slightly less than 8 centimeters, but again, 8 centimeters would be acceptable. Okay, if you write down less than, if it's 7.8 for you, 7.8 centimeters, it would be acceptable. But I will just use 8 centimeters for this experiment. 8 centimeters. It's nothing wrong with your ruler, it's just something wrong with the printing of this paper. Figure 3.1 is 1/10 the actual scale. 1/10 the actual scale. So it's actually smaller than the actual scale. It's smaller than the actual reading by 10 times. So if I want to find the actual reading, I need to multiply by 10. So if it's 1/10, you need to multiply it by 10. 8 times 10, which is 80 centimeters. Okay, if the question was saying 1/5 the actual scale, so you need to multiply by 5, because this is a scale diagram. We've scaled it down by how many times? By 10 times. It's a smaller reading. Calculate and record in table 3.1 the focal length using this equation, UV over capital D. Okay, UV over capital D. What is U and what is V? Okay, divide by capital. You have U and you have D. You have U and you have V divided by capital D. Please take care that it is actually what? It's actually capital D, which is 80. Again, what will I do? I'll just multiply. You will just multiply 59.8 times 20.4. 59.8 times 20.4 divided by 80. Okay, divided by 80, which is 15.2. 15.2. And then for the second row, can I do the same? Yes, you can do the same. 19.8 times 60 divided by 80. Using your calculator, it would be 14.9. Okay. You didn't come up with any new equation. He gave you the equation UV over E, UV over D. And he was very specific. He said capital D, not small d. So the capital D is actually 80. You need to divide by 80. Calculate the average value, FA, of the focal length of the lens. Can I find the average value? Yes, the average value. Average, anything would be just adding these two numbers and dividing them by 2. So 15.2 plus 14.9 divided by 2. This would give you 15.05. Or you can just write it down as 15.1. Because we need 3 significant figures. 15.1. State one precaution that you would obtain. What is one precaution that you would take to obtain accurate measures? Yes, using a dark room. Use a dark room. Another student wants to obtain more measurements for U and V. The student moves the screen to a distance of 40 centimeters to the right. Okay? 40 centimeters. He moves the screen 40 centimeters to the right. What would the new distance for D be? What would the new distance of D actually be? If you move the distance, if you move the screen to the right, the actual distance d was what? Was 80 centimeters, right? So small d was 8 centimeters, capital D was 80 centimeters. If you move the screen 40 centimeters to the right, so the total distance would be what? Just add 40. Just add 120 exactly. You just add 40, so it's 120 centimeters. 80 plus 40. This one moves the lens to a new position, has a new V and a new U. Can I find F? Okay, what is the new focal length? F, basically 22.2 times 97.9 divided by 120. Again, it would give you a focal length of 18.1. 18.1. Why should I use a dark room? Because this is an image produced by an illuminated object. It's like having a projector in a classroom. For example, when you switch on the projector, it would be always better to have a dark room. To produce a very clear image, it would be better to have a dark room. State and explain briefly whether the values for FA and F are the same within the limits of experimental accuracy. What was FA, the average focal length, 15.1, and the new F is 18.1. Are they within the limits or not? Let's calculate it. Okay, calculate. So it's basically 18.1 divided by 15.1. What's 18.1 divided by 15.1? This is 1.19. It's 1.19, meaning that this is a 19% difference. This is a 19% difference, which is definitely unacceptable. It has exceeded the limits. So no, okay, not the same value. Okay, not equal. Why? Because the values are far apart. Values are far apart, exceeding the limits of exceeding the limits of experimental accuracy. Maximum limit could be up to 15. That's if we push it. If you push to be on the safe side, the limit would be up to 10%. What if it's between 10 and 15? This is a very gray area. If it's between 10 and 15, this is a gray area. It could be considered yes or no. If you write yes with the correct explanation, it would be correct. If you write no with the correct explanation, it would be correct as well. Okay? Now, a student investigates the time taken for the ice cubes in a container to melt using different insulating materials on the container. The following apparatus is available. Student can also use other apparatus and materials that are usually available in a school laboratory. Plan the experiment to investigate. Plan the experiment to investigate the time taken for the ice cubes to melt using different insulating materials. So it's quite simple. You need to find the time taken. This is the output. Based on the input or the different things. What's the thing you're changing? Insulating materials. Insulating. So what is the range of values? What is the independent variable? What is the thing that I am changing? The insulating materials wrapped around the container. Okay? Insulating materials wrapped around. Draw a diagram of the apparatus used. So how can I draw a diagram of this apparatus used? All you need to say is you have the copper container. So let's draw it. This is the copper container. Okay, inside the container you have some ice cubes, right? You have some ice cubes. So these are the ice cubes. And then this is the container or the copper container. And then what about the insulating materials? What should I do with these insulating materials? I need to wrap the copper container with these insulating materials. Okay, you need to just wrap it with the different insulating materials. So I'll put the insulating material all around the container. So this is the insulating material. Have the insulating material all around the copper container. What is the range of values? What is the independent variable? Okay. No, you have a copper container and you're wrapping around it the insulating materials. Okay. Range of values. Okay. Range of values. You have the different insulating materials. Insulating materials such as, you can say cotton, you can say wool, you can say plastic, right? Wood. You can say wood, for example, you get a wooden container, which is exactly the same size, or you can say glass, for example, whatever insulating materials, polythene, whatever you can come up with. These are the different insulating materials. Okay, so these are, I've written or I've drawn the apparatus used. And then state the key variables. What would the key variables be? What would the constants, the controlled variables? What are the controlled variables that we have? What are the constants? Yes, the same volume of ice. Okay, same number of ice cubes, same volume of ice, or same number of ice cubes of ice cubes, same volume of ice. You can also say same initial or same room temperature, same room temperature. Okay, yes, these are the controlled variables. I don't need to add any additional apparatuses. Why? Because he's already given me a thermometer, a stopwatch. That's all you need to have. Okay, that's all you need for this experiment. And then, what about the steps? What about the steps? You just need to put the cubes in the container, right? You have the insulation wrapped around the container, and then you can, okay, add the cubes to the container or in the container, and then start the stopwatch. Start the stopwatch. Measure the time taken for the ice to melt. Measure the time taken for the ice to completely melt. Okay, need to measure the time taken for all of this ice to melt. And then repeat for different insulators. For different insulating materials. Okay, then for the table. Okay, so we've drawn the diagram. Should I add the thermometer? Yeah, you can if you want to. Okay, you can put the thermometer in the ice, for example. You're not actually measuring the temperature, but if you want to, you can put the thermometer as such. This is the thermometer. Okay. What about the table? Can I draw the table and then write down a conclusion? Yes, the table has only two. Okay, table. So this is the insulating material. Insulating material. And then you have the time taken in seconds or in minutes. It doesn't really matter. And then last but not least, can I write down a conclusion? Yes, for each material, for each insulator, repeat the experiment, and take average, and then compare or record the readings in the table. Okay, record the readings in the table. When you record the readings in the table, compare the results. Compare the results using a graph. Okay, compare the results using a graph. Okay. Okay.